Thus begins the first of 4 videos on solution chemistry, mixtures, and concoctions. Let's start with a few definitions. There are some key terms you need to know when talking about solutions. The first is the solute. That's the substance being dissolved. So you can think about making a big pitcher of Kool-Aid, and that Kool-Aid powder would be your solute. The solvent then is what we dissolve the solute in. So again, if you're thinking about Kool-Aid, that's that big pitcher of water. And then when we put the two together, when we mix the solute and the solvent, we get our solution. Let's look at what's happening during solution formation. So here we have a solution of salt water being formed, and on the left side we have solid sodium chloride in its three-dimensional crystalline structure. When you put those salt crystals in water, water is a polar molecule, it has a positive side and a negative side. That negative side will line itself up and attack those positive ions in the crystalline structure. The positive side will align towards the negative ions, and then those ions will be pulled off of that crystalline structure, and you will then have aqueous sodium chloride, which is a solution of ions surrounded by water molecules, as you can see there on the right. Those ions, when they are dissolved in water, are referred to as solvated ions. So once they dissolve and they're surrounded by those water molecules, we refer to those as solvated ions. While we're looking at this situation of ionic compounds dissolved in water, let's kind of look back a little bit at reaction types. And so you may remember we talked about double replacement reactions in aqueous solution. And so here we have a reaction involving sodium chloride. And then if we add solid silver nitrate to solid sodium chloride, well, those ions are locked in their crystalline structure and not a whole lot is going to happen there. However, if we take that that same sodium chloride and dissolve it so that it's in aqueous solution, and we mix that with an aqueous solution of silver nitrate, now those ions are free to move about. And we find when we look at our solubility table that silver chloride is insoluble. So as those ions find each other in solution, they're going to form solid silver chloride and precipitate out. But this process will only work when you do this reaction in solution and those ions are free to interact with one another. We could also look at non-ionic compounds and look at what happens when they dissolve in water. So we know that sugar dissolves in water, and it primarily does so because it is polar. And so here we have the sugar crystal on the left side, the solid C6H12O6, and we would dissolve it in water. We get a similar process here, but rather than break it up into its parts, it's just going to pull those individual sugar molecules where the positive sides of the water molecules are going to align towards the negative part of the polar sugar crystal, and the positive parts of the water are going to align themselves to the negative side. I think I was a little bit redundant there, but you get the idea. And this all works because of one of kind of the generalized solubility rules that like dissolves like. Polar and ionic compounds tend to mix pretty well. Non-polar compounds tend to mix with other non-polar compounds, but polar and non-polar do not mix. And here we have an image of oil and water. Water is a polar molecule, whereas most fats and oils are non-polar molecules. When we have liquids, like we do in this picture, that don't mix, rather than soluble and insoluble, we sometimes use the term miscible and immiscible. Miscible meaning two liquids that will mix or will dissolve in one another, and immiscible meaning two liquids, oil and water, that will not dissolve. Another term that we might take a second to look at here is a thing called a surfactant. A surfactant is a substance that lowers the surface tension between two liquids. A surfactant is a fairly large long chain molecule that has one polar side and one non-polar side. And so this little zigzag you see here is a chemical structure where carbons and hydrogens are to be found at each of the points of that zigzag. This is a structure that we would refer to as sodium stearate, and this is a fairly simple compound that would be found in most soaps. And so what you have with a soap or a surfactant is the nonpolar substances will mix on the nonpolar, that long chain to the left, and then the polar substances will mix or react with the polar side on the right, that COO minus, or that ionic side. And so what happens here when you wash your hands with soap is that the water from the sink is mixing with the oils from your hands, and any other dirts and germs that are on there are going to be washed away with that oil and water mixture. This is also, by the way, if you wash your hands very frequently, which you should be doing right now, that you end up getting dried and chapped hands because you're constantly taking that oil layer off the top of your hands. All right, we're going to wrap this particular video by talking about the factors that affect the rate of solution formation. This is not talking about what will or will not dissolve. If you have an insoluble substance, say in water, no amount of changing those conditions are going to make that insoluble substance soluble. But if you have a substance that will dissolve in another substance, we can talk about how fast those solutions will form. And so there are three factors that affect the rate, or how quickly something will dissolve. The first is fairly straightforward. It's agitation. So if you're having a cup of tea and you want to put a bit of sugar in your tea, stirring it or swirling it or shaking it is going to make that sugar dissolve much quicker. The second is temperature. At high temperatures, things tend to dissolve faster than at low temperatures. And this, of course, shouldn't be surprising when we consider the thermodynamic definition of temperature as the average kinetic energy of particles in a sample of matter. So high temperature water has molecules that are bouncing back and forth really quick, and they're bumping into the surface of those solids way more frequently. And so the process of solvation is going to be faster at higher temperatures than it will at lower temperatures. Particle size. So we're not talking about the particles, the size of the molecules themselves, but we're talking about the larger larger clusters. So again, if we think about that idea of having a cup of tea and dissolving sugar, well, we can either take granule sugar or sugar cubes, and a sugar cube has a much larger particle size, meaning a lot of the molecules are on the interior of that structure. And so the rate at which the solvent molecules are going to bounce into those sugar crystals are going to be much slower or much fewer than the particle size, or than that same solvent bumping into the sugar crystals on the bottom of that picture. One of the ways to go from the large sugar cubes to the granule sugar is to use a mortar and pestle. And so there's a pretty standard first year college chemistry lab where you figure out how much acid it takes to neutralize antacid tablets. And inevitably, one lab group is going to take those antacid tablets that they're given by their lab instructors, they're going to drop them in a cup of water, and they're going to sit there and they're going to stare at them. Because they are going to dissolve very, very slowly. And some other group is going to remember their high school chemistry course. They're going to take out that mortar and pestle, and they're going to crush those tabs down into a powder, and then they're going to dissolve them in the water. And they're going to find that process is much, much quicker. And they're going to have their lab done. They're going to be cleaned up, and they're going to be out the door to enjoy the rest of their day. While that group that just dropped those two large antacid tablets in water are going to be there for quite some time waiting for those tablets to dissolve. So those are the factors that affect the rate of solution formation.